Welcome to this explainer. Today we're diving into something that's going to fundamentally change how you think about algorithms, data, and problem solving in general. We are tackling recursion. Now, I know, this concept is notorious for twisting programmers' brains into absolute pretzels. And honestly, it's responsible for some pretty terrible computer science jokes. But don't worry, I promise you it doesn't have to be this mysterious, intimidating thing. By the time we wrap up, you're going to see just how incredibly elegant this concept truly is. We're literally unpeeling the logic of recursion.
Here's our roadmap for today. We're going to start with the pattern around us, then move into unpacking the logic. After that, we'll look at real-world software, tackle some common misconceptions, discuss why recursion matters, and finally, wrap up with the building blocks of algorithms. This is going to help us take a daunting concept and break it right down into an intuitive tool.
Section 1. The pattern around us. The pattern in nature.
So before we look at a single line of code, let's anchor this abstract idea to things we've literally all experienced. Picture this. Have you ever stood in a hallway or maybe a bathroom, perfectly positioned between two parallel mirrors, and you see that infinite tunnel of your own reflection just stretching out forever? Or think back to when you were a kid playing with a set of Russian nesting dolls. Every time you open one doll, boom, you find a slightly smaller, identical doll sitting right inside it. Well, if you've seen that, your brain already understands recursion. It's not just some obscure programming trick. It's a self-similar pattern that existed in the physical world way before it was ever typed into a computer.
And this self-similar pattern really does show up everywhere. You see it in branching tree fractals, the intricate arms of a six-sided snowflake, repeating honeycomb structures, you name it. But let's look at a totally relatable, everyday human example. Imagine you're standing in a massive, crowded supermarket checkout line. You desperately want to know exactly what number you are on this line, but you can only talk to the single person directly in front of you. So, what do? You ask them, "Hey, what number are you?" Now, they don't know either, so they ask the person in front of them, who asks the person in front of them, and so on. This chain reaction keeps happening until the question reaches the very first person at the cash register. That person says, "I'm number 1," and passes the answer back down the line. The second person adds 1 and says, "I'm number 2," and it cascades all the way back to you. Figuring out your place by asking a smaller version of the exact same question? That is a perfect analogy for how recursive problem solving actually works.
Section 2. Unpacking the logic. How recursion works.
Okay, let's translate that real-world pattern into a foundational computational tool. Here's our formal definition. Recursion is a function that solves a computational problem by calling itself on a smaller version of the same problem. So rather than trying to swallow a massive, incredibly complex computation all at once, the algorithm acts kind of like a sculptor chipping away at a block of marble. It does a tiny, manageable piece of work, and then it literally hands the rest of the problem off to a brand new, fresh instance of itself. It's really the ultimate expression of the divide and conquer strategy.
Now, there are two absolutely crucial parts to this. The first is the base case. This is the mandatory stopping condition where no further work is required. Think back to our supermarket line. The base case is that very first person at the register. They don't have to ask anyone else, they just know the answer. If your recursive code doesn't have a base case, well, the function will just keep calling itself into an infinite void, which we definitely don't want.
The second essential part is the recursive case. This is really the heart of the engine. It's the part of the code where the function performs a minimum amount of work, just the absolute smallest logical step, breaks the remaining problem down, and then calls a fresh version of itself to handle the rest. By perfectly balancing these two elements, the recursive case to actually do the work and the base case to stop it, we can solve incredibly complex puzzles.
Let's see how this logic builds visually using a classic math problem, calculating a factorial. Let's say we want the factorial of 5, which, as a reminder, means 5 times 4 times 3 times 2 times 1. Our function starts with step 1. It basically says, look, I don't know the whole answer, but I know it's 5 multiplied by the factorial of 4. So it creates a pending multiplication and calls itself. Step 2 does the exact same thing, holding on to the number 4 and asking for the factorial of 3. Step 3 holds on to 3, step 4 holds on to 2. What's actually happening inside the computer here is that these function calls are stacking up, one right on top of the other in an isolated environment in your computer's memory called the call stack. Every single step is just hanging out waiting for an answer. But then, our descending stack of pending math hits factorial 1. Boom! We've officially reached our base case. The function inherently knows that the factorial of 1 is just 1. It doesn't need to call itself anymore. It safely stops that chain reaction and simply returns the number 1.
And here is where the magic happens. The stack unwinds, resolving the problem from the bottom up. The base case returns 1 to the frame waiting right above it. That frame multiplies 2 times 1 to get 2 and then pops off the stack. The next frame takes that 2, multiplies it by its 3 to get 6, and pops off. 4 times 6 is 24. And finally, that very first function call sitting at the top of the stack gets the answer it's been patiently waiting for. 5 times 24 equals 120. The original problem is completely solved.
Now, it's not all sunshine and roses. If you make a mistake, you might encounter the dreaded stack overflow. This is a total execution failure, caused when a program's call stack exhausts all of its allocated memory. Basically, if you forget to write that vital base case, your function has no idea when to stop. It just keeps adding frames and appending operations to the call stack until the computer literally runs out of space, overflows, and crashes the program entirely. Honestly, doing this is practically a rite of passage for every programmer.
Section 3. Real-world software examples. Recursion in action.
So, we've talked a lot about math, but this invisible recursive logic is actually running inside the applications you interact with every single day. Make no mistake, this isn't just an academic exercise. Whenever you open a file explorer on your computer to dig around for a document, you're navigating folders inside of folders inside of folders. Because the computer doesn't know in advance exactly how deep those folders go, it relies heavily on recursive algorithms to elegantly traverse those unknown repeating depths. We also see recursion constantly when parsing structured data trees like JSON or XML, or even when an app renders nested UI components. Think about a social media comment thread that has replies, inside replies, inside replies. Yep, recursion is running invisibly everywhere.
Section 4. Common recursion misconceptions. Myths versus facts.
Because recursion is notoriously powerful, it's also highly misunderstood. Let's tackle some of the biggest myths. One incredibly persistent myth is that recursion is always slower and fundamentally worse than using a standard loop. Well, there's definitely nuance here. Factually, yes, standard recursion uses more memory because it creates new separate stack frames for every single call. However, recursion provides an exceptionally clean and robust structure for handling highly complex branching data. When you have a messy problem that would require incredibly convoluted, hard-to-read loop logic, a recursive solution can often distill it down to a few elegant, highly readable lines of code. It's really about choosing the right tool for the specific data structure.
Another massive misconception is that recursion is just a fancy way of looping. But look at the actual structural difference here between iteration and recursion. Iterative loops, like your standard while or for commands, use simple control structures within the exact same memory space. Recursion, on the other hand, relies entirely on the computer's call stack to manage state. Every recursive call creates a fresh, isolated local environment for its variables. Recursion literally lets the system handle the memory state for you. Finally, there's this myth that you absolutely need recursion to solve every complex problem. In reality, recursion is just a tool. It's not always the best one, and technically, any recursive solution can be rewritten iteratively. Again, it usually comes down to prioritizing readability versus memory.
Section 5. Why recursion matters. Mastering the concept.
So why should anyone learning computer science or working in tech spend the time to truly master this? Because mastering recursion fundamentally changes how you approach breaking problems down. It is the absolute gateway to foundational computing concepts. You really cannot efficiently build or search complex trees and graphs without it. It's the core of executing advanced divide and conquer algorithms, unlocking dynamic programming, and, let's be real, acing those notoriously difficult technical interviews. Once you train your brain to decompose a massive, intimidating problem down into one tiny sliver of work and a base case, your entire paradigm of problem solving evolves.
Section 6. Building blocks of algorithms. The final reflection.
As we wrap up this explainer, I want us to reflect on the profound elegance of this computational tool we've just unpacked. The renowned computer scientist Nicholas Wirth famously observed, "The power of recursion evidently lies in the possibility of defining an infinite set of objects by a finite statement." Just let that sink in for a second. Recursion is essentially infinite computing power, gracefully contained within just a few simple, well-designed lines of code. It's pretty amazing when you think about it. So, I leave you with this thought. How will you break down your next complex problem? Whether you're writing code or just navigating life, maybe there's a base case hiding in there, just waiting to be found. This explainer is just the first building block in a much larger series exploring how algorithms actually think and operate under the hood.
Thank you for watching The Tech Canvas. Complex ideas, clear pictures. Follow for more.